All right, we are going to review a derivative at a point and also find the derivative at any x. This is the 2.8 pre-class video. So remember, we had this as our derivative evaluated at a. It's the limit of this ratio as x approaches a. And we had another way to write this derivative evaluated at a, and we did that by making a substitution. Let x minus a equal to h, so that's the denominator. Let that be h. Then we can rearrange this and solve for x, and therefore x is equal to a plus h. And notice, as x approaches a, that would mean h goes to 0, right? As x approaches a, x minus a becomes really small. That means h goes to 0. And so plugging in the substitution, plugging in h for the denominator and a plus h in for x in the numerator, and h approaching 0 instead of x approaching a, we have this other form, which also gives us the derivative evaluated at a. Then what we did next is looked at a particular function, a function like x squared, and we found the derivative at a particular point. Say the point 1, 1. Well, there's our derivative, and we'd still have to evaluate that limit. But we could do another point, say the point 2, 4, or how about 3, 9, or 4, 16, or the point 5, 25. And how about instead of evaluating this limit every time we want to find the derivative at a particular point, we just find the derivative once. So notice we're evaluating our function at various points. Let's put in a variable into this limit. So notice the connection now between this limit with an x in it and what we had before. And let's see what happens now when we evaluate this limit. Well, if I multiply that top out and simplify the numerator a little bit, those x squareds disappear, and we can factor out that h. And that limit turns into the limit of 2x plus h as h approaches 0, which turns into 2x. Now this is really cool. We know the derivative of x squared at all values of x. Imagine geometrically what this means. Well, for our function x squared, we know all the slopes of all the tangent lines that we could put on this function x squared. And how about physically? The interpretation would be, well, if this function x squared is modeling something, we know the instantaneous rate of change at all values of x. So that's pretty sweet. So from now on, you don't really want to think about taking a derivative just at a particular point, but taking the derivative of a function at all values of x. All right, so hopefully this has warmed you up for this next class.